Okay, so why don't we go ahead and get started? First, I want to welcome you to this Radio Shop chat organized by SpectrumX, the NSF Spectrum Innovation Center. My name is Scott Palo. I'm a professor in the SMED Aerospace Engineering Sciences Department at the University of Colorado Boulder, and also serve as Associate Director for SpectrumX. And I'm going to be your host for this Radio Shop chat today. Before we get started with the Radio Shop chat, I just had a couple of items to share with you. So I think, Julia, if you want to move on to the next slide. So first, I want to remind everybody that SpectrumX is the world's largest academic hub through which all stakeholders can collaborate and innovate to make the best use of the precious radio spectrum to benefit society. We have a robust group of partners within SpectrumX, a large number of research institutions, students, faculty, research staff, external advisors, all working hard together to understand the challenges and to bring new insights and ideas to how we can work together to address these challenges going forward. Next slide, please, Julia. So to give you an overview, the purpose of these Radio Shop chats are to bring the community together to educate, debate, and inspire in the next steps of collaborative research, workforce development, and policy outreach. So we're here to bring the community together to hear about an interesting topic and to get input. So we have a couple of speakers I'll be introducing in a minute, and I just wanted to point out the third item here that Radio Shop chats follow the Chatham House rule, which means that participants are free to use the information received, but neither the identity nor the affiliation of the speakers nor of any of the other participants may be revealed. So next slide, please, Julia. So if you want to learn more about SpectrumX, you can follow us on our website, LinkedIn, or we also have a SpectrumX store if you want to get cool swag from SpectrumX. So once again, thank you for participating, and we hope you enjoy today's chat. And please spread the word about SpectrumX and the Radio Shop chats. Next slide, Julia. So let's get into our talk today. We're very excited to have a couple of esteemed colleagues here to talk to us about the views of the National Academies of Sciences, Engineering, and Medicine on agenda items at issue at the World Radiocommunication Conference in 2027. We have co-speakers. We'll be starting off with Nathaniel Livesey, who's a senior research scientist at the Jet Propulsion Laboratory with the California Institute of Technology. And he'll be partnering with Scott Paine, who is a senior physicist at the Center for Astrophysics at the Harvard and Smithsonian. And so with that, I will turn the floor over to Nathaniel for any additional introductions and to get into the chat. And I will maybe also mention, if you have questions, comments during the chat, please, during the talk, please drop them into the chat or raise your hand. We're happy to make this interactive. It doesn't have to be, a 30 or 40-minute seminar. So if you have questions, raise your hand. I can call on you. Additionally, if you put them in the chat, we can also call on you, or I can bring them to the attention of the speaker. So, Julia, if you would stop sharing, and we can turn it over to Nathaniel.
Great. Thanks, Scott. Let me just pick the right application to share. Okay, I think you're seeing that. And if I go into slideshow mode, right. Okay, is that now working properly?
Yes, we are seeing your screen.
Great. Thanks, Scott. Thanks for the introduction. So, yes, I'm Nathaniel Livesey. I'll give a brief introduction of myself and then turn over to Scott. First, I want to say that, Spectrum is not my day job. Neither is it Scott. I work on Earth remote sensing. In most of the time, I involved in a mission that's looking at atmospheric chemistry by scanning the atmospheric limb, the edge of the atmosphere out of the front of the spacecraft, in a range of frequencies from 118 gigahertz to 2.5 terahertz, looking at things like ozone layer recovery and so on. I'm here because I was chair of the committee writing this report, and also a prior chair of the Committee on Radio Frequencies. We'll talk about what that is later. And Scott, why don't you give a brief introduction to yourself too?
Sure. I'm Scott Paine at the Smithsonian Astrophysical Observatory, which, as Scott mentioned, is a part of the Center for Astrophysics here in Cambridge. My work has been on instrumentation for submillimeter astronomy, particularly the submillimeter array in Hawaii. I've also done work in spectral radiometry of the Earth's atmosphere, and now spend most of my time on experimental cosmology, also at millimeter wave frequencies. So back to you, Nathaniel.
Thanks, Scott. Yeah, so this report was written by a committee that is to large order was a snapshot at the time of the Academy's Committee on Radio Frequencies. As I say, I'll talk a bit more about that later on. And the Committee on Radio Frequencies is roughly 50-50 people doing astronomy. So that's the RAS designation you see there, and Earth remote sensing. So that's EESS. And you can see we have a kind of a mix there. We had an additional member, Julio from Boeing, who gave us some help on instrumentation and RFI issues from the industry perspective. We're also greatly aided by a former CORF colleague, Darrell Emerson, who retired before this committee was formed. And if many of you haven't met Paul Feldman, I commend him to your acquaintance. He's the legal counsel and the driving force behind CORF. I think he's online today, and I saw Arul is online. He is I think the associate director for now I think acting director, right, for the Board on Physics and Astronomy. So welcome, Arul, and thanks to the Academy staff for all the help putting this report together.
So Nathaniel, I was just going to interject just briefly on a housekeeping issue. I don't know, Rich Lee, if you can hear me, but you've got a hot camera, so you may want to blank your camera there.
Thanks, Scott. Okay, so some introductions first. So I imagine a lot of this will be familiar to many of you, but we put it in anyway. So the World Radiocommunications Conference happens on a regular basis. The radio spectrum, as you know, is shared between commercial, government, and scientific users. And because radio signals freely cross over national boundaries, obviously international coordination is essential. Hand in hand, of course, with domestic regulations like FCC, NTIA, and so on. Now, the radio regulations are many thousands of pages, split into like 5 huge PDF files, and they're agreed upon at these World Radiocommunication Conferences. Revisions to these regulations, though they're incremental because the regulations are so large, you can only change them, a few places at a time. So every 4 years or so, the World Radiocommunication Conference meets and agrees incremental changes to the radio regulations through specific agenda items, AIs. You'll see that a lot here. And there's 19 of them for WRC 27, and they cover a whole range of the spectrum, users, as we'll see. And so they really, and each of these agenda items has multiple ramifications affecting many different interests. So it takes a lot of negotiation over the 4 years between the conferences to really hone in on what the right answer is, where right is defined by the beauty of the beholder and so on. And we're writing this report from the context of the views of the National Academy of Sciences for the scientific use of the radio spectrum, mainly purely for observation. So the passive and to some extent active use of the radio spectrum for observing either the universe or planet Earth. We don't focus anything to do with downlinks, for example, for Earth orbiting science satellites. It's just purely the bands used for observation that to large order are there because that's where Mother Nature put the useful part of the spectrum. The L band is really great for doing soil moisture, for example. Water vapor has molecular lines in particular regions, so then you can't necessarily move to other channels to get the same science. So this report that we've written reviews the agenda items for WRC 2027 and discusses the potential impacts on the scientific use of the spectrum for radio astronomy and Earth remote sensing. This report was released in May, and I've lost count of the number of times that Scott and I read every word beforehand. In the time since then, I've not read it so much, and a lot has happened, I'm sure, with everybody here on this line. A lot of existential challenges in going on with government-funded science right now. A lot of that's put this out of my mind. So apologies if some of my memories here are a bit rusty on the individual agenda items. We do have slides on every single agenda item. We're not going to show them all, but if we want to get to other ones during the time, we can go to those. I'm not sure, Scott, whether the package will be archived online. I'm happy for that to happen. The report is available now. It's available online at the National Academy's website. I should have put the QR code for that up. There is also a paper copy, which I think I've heard report of somebody holding one in front of a camera. I've not seen it myself yet. So that's what the report's about. So just a reminder here on the value of the scientific use of the spectrum. Radio frequencies play a vital role in scientific discovery. We've had multiple Nobel Prizes awarded for radio astronomy discoveries, and many key Earth science studies have been informed by remote sensing observations using the radio spectrum. And as I alluded to before, the scientific use divides, for our purposes, into two main services. The radio astronomy service, RAS, is what we use to probe the origin and evolution of the universe, the chemistry and the formation of stars, solar systems, planets, so on. And then matter in extreme environments, also gravitational radiation and solar activity. We're now seeing with these gravitational measurements, we can then go and quickly look at them in other parts of the spectrum. A good look at the region of the sky that's getting us interested in, from a gravitational perspective, just quickly zoom in on what's happening with the electromagnetic spectrum, including at the radio wavelengths. The Earth remote sensing is carried out in what's called the Earth Exploration Satellite Service. This is a critical tool for predicting weather and diagnosing many aspects of the Earth system, such as soil moisture, ocean surface winds, and so on. Satellites provide data valuable for societally important issues, including food security, transportation, energy, national security, and so on. And Earth remote sensing is done both in the passive and the active mode. So there's lots of passive radiometers, and there's quite a few radars as well. They're different wavelength regions. Together, this work represents billions of dollars in federal investment and numerous satellites, radio observatories in various locations throughout the world, and so on. And of course, similar levels of investment from other countries and regions. Just some little eye candy here on the right-hand side for both radio astronomy and Earth remote sensing of the kind of information we can get from these observations. Now, two really key points here. As I'm sure you know, the signals that we measure in radio astronomy and Earth remote sensing are very small. They're easily overpowered. They are what commercial users of the spectrum would consider the noise. When people ask us what the signal to noise ratio is, we have to say, no, you don't understand. We're measuring the noise. But as important as those signals are, and as small as they are, we know that they're there. The question is not whether we can detect them. We need to be able to measure them to very fine levels of precision. So this picture on the right here is the canonical image of the microwave background radiation. What you're seeing here is the color scale is so incredibly zoomed in. These are 0.004% fluctuations in the cosmic microwave background signature. You have to integrate for days to get this level of precision. I think days is right, Scott. And so talking about any delta T is not necessarily a useful measure. You have to think about the systematics. And one of the systematics is radio frequency interference. Similarly, on the Earth remote sensing side, a 1 degree Celsius change in say, ocean surface temperature is about a 0.3% signal level change. It's 1 Kelvin out of 300 or so. So you're looking for these 0.3% changes in, an already small signal that will help you understand and reliably predict, for example, the trajectory of a hurricane. So these observations are very faint signals that need to be measured very precisely, very accurately. Actually, more accurate. The precision is kind of what we get from the detector technology we're using. It's the accuracy that we really care about, because that's what matters when we average it out, when we integrate for long periods. So these passive observations need to be protected. That is done through multiple routes. In the first order, it's through designating specific bands for specific services, including radio astronomy and Earth observation. And some of these bands are afforded what's called all emissions prohibited protection under RR 5.340, a footnote that basically says in these bands, all emissions are prohibited. For radio astronomy, there are coordination agreements in place for many observatories to make sure that local sources of emission from communications providers, power companies, and so on are kept to a minimum in these, particularly in what's called radio quiet zones. But as we know, there's been rapid growth in air and spaceborne transmitters, and they're presenting a challenge to maintaining these quiet zones and these coordination agreements. It's one thing to coordinate with a local fixed or even somewhat mobile operator. When you've got airplanes flying overhead, satellites in the sky, all beaming down, that's going to be a much harder thing to protect, and we'll talk about that later on. So despite these protections, RFI is common. This is a picture here, a metric here of how often NASA's SMAP mission detects signals that shouldn't be there in the 1.41 gigahertz band that is one of these all emissions prohibited. This is a band that we use for measuring soil moisture. It's actually protected mainly for radio astronomy because it's a very important line for hydrogen. But we take advantage in the Earth remote sensing arena of that protection because it's also a good region for measuring soil moisture and other parameters. So these regions you see here glowing are a non-natural signal in a band that is marked all emissions prohibited. So clearly there's either some bad tuning or some leakage from out of band emissions or something going on. And in many cases, these are addressed in Japan. For example, I believe it's an annoyingly faulty satellite TV setup that there's now a buyback program in Japan where people can exchange their boxes, but it's going to take a while before that signal clears away. Now, strong RFI corrupts observations in recognizable ways. We can just like here, this was a metric we can say this is an aggregate over a period of time, but individual measurements, we can say this one was contaminated, delete it. We cry over our beer on that. It's lost information. It shouldn't be happening in the protected bands, but at least we can recognize it for what it is. And we should try and discourage it in cases when it's in violation of the international radio regulations. At the other end of the range, in principle, very weak levels of interference can be tolerated if they genuinely have no impact on the scientific measurements. But as we talked about in the previous slide, if you're integrating for many hours, it's not clear that there is really a threshold that is acceptable there. But the greatest threat comes from RFI that's actually sitting right in the middle. It's strong enough to corrupt the measurements, but it's not easily recognizable at face value. And so if it's ingested into a weather forecast, for example, it could lead to incorrect conclusions or incorrect forecasts. In astronomy, you could draw the incorrect conclusions from this, this observation. Just a bit here about some of the fundamentals. In observing the universe in radio astronomy, the radio wavelengths offer a view across the entire cosmos and into dust-obscured regions. This is a particularly important point. Same with Earth remote sensing. The optical wavelengths are obscured by dust in the galaxy. They're obscured by clouds and dust on Earth. And so these radio frequencies, because they're long wavelength compared to the optical wavelengths and the infrared and so on, can see through those into the regions where these astronomically important processes taking place. These wide range of angular scales observed from sort of full sky surveys to really precise, incisive views of very narrow regions. We make use of observations of continuum all the way out from megahertz to terahertz here. You can see how this sort of fingerprint of different processes going on in the universe map into the different wavelength regions, and by looking at combinations of frequencies, you can disentangle these various processes. The same is true in Earth remote sensing, as you'll see in a minute. And then when you zoom in and you get this wonderful richness of molecular spectrum, you can see here how detailed we can really get a sense of the chemistry of our universe, of solar systems, of star forming regions, and so on. Similarly, in Earth remote sensing, we make use of a broad range of frequencies. The various properties of the Earth system, temperature, salinity, soil moisture, clouds, etc., they're all intertwined and have these smushy overlapping footprints. Less so perhaps for the molecular species, but in the atmosphere, but for surface properties, for water vapor, for all these other things, there's these various fingerprints, and no one single band gives you a sort of unique unambiguous view of a particular parameter. Rather, you have to look at multiple bands at the same time and sort of do the matrix inversion to work out what are these various things. What is the soil moisture? What is the surface roughness? What is the humidity, and so on. So loss of measurement in an individual band kind of undermines the value of the whole observing system. So we really need to try and protect these bands as an observing system. Brief aside here. So the Academy's Committee on Radio Frequencies, CORF, is the sort of the parent committee for this report. CORF represents the interests of US users of the radio spectrum for astronomy and earth science, both basic and applied. We coordinate the views of US scientists and act as a channel to represent their interests. We recommend requirements and limits necessary for protecting scientific use of the radio spectrum from interference. And our day-to-day work, I say I've now stepped back from CORF. Scott is still involved. But the day-to-day work of CORF is largely through filing comments in the public proceedings of the FCC. So the FCC puts out an NPRM, a notice to propose rulemaking, and we write comments with the aid of our legal counsel, Paul. And then these have to be reviewed. These are National Academy products. They have to be reviewed, peer-reviewed externally, and then signed off up the various levels of the National Academy signature. And that's usually a process for most reports that takes months. The FCC gives us 30 days, maybe 60 days. So as you can imagine, we're really grateful to the Academy staff for really greasing the skids, and we're grateful to the standing board of reviewers we have ready to turn around quick responses on our filings with the FCC. We also do specific studies, including the views report that you're seeing here, and we maintain a handbook, although that's getting quite aged now, and conduct various forms of outreach to scientists in industry, including talks like this. So now we're going to turn over to the meat of this presentation, which is the Walk 27 agenda items. I perhaps have gone faster than I thought I would, but we will see how this goes. So here's a figure that we put together that lists down the side here each of the agenda items. So all the Walk 27 agenda items are 1 point something, and then down on the far right is just a little sort of rather cryptic an inside baseball summary of what each one is about. And then the x-axis here is frequency, and you see here for each row there's some gray bands here. They show what are the bands under consideration in this agenda item. So agenda item 1.7, for example, considers new allocations to IMT, International Mobile Telecommunications, what you and I know as cell phones. So it's looking in these bands here. And then in purple, we've plotted the bands allocated to radio astronomy that are adjacent to one of those bands under consideration. Similarly, in green, we show bands that are allocated to Earth remote sensing. And then in orange are these all-important RR 5.340 all emissions prohibited bands, just the sort of the most protected of the bands. And I say here for the green and purple, actually, most of these are allocations. Some of these are all instead just little footnote mentions in the radio regulations, and figures you'll see later on go into just differentiate between those. So you can see here just the range of frequencies being addressed by the Walk 27. So you go down to a few megahertz here for agenda item 1.9, which is looking at mobile communications for aeronautical services and so on, all the way up to the terahertz, looking at radio location at high frequencies, new services for standoff threat detection and so on. And we looked at when the agenda for Walk 27 came out, Scott and I looked through it, and we decided that pretty much all but 2 or 3 of the agenda items had the potential, as you can see from this figure here, given their adjacency to radio astronomy or Earth remote sensing bands. Many of the agenda items, all but a couple of them, have the potential to affect scientific use of the spectrum. So we had to do an assessment of the potential impact of each of them. And in the report, if you download it, you will see in each case, for each agenda item, we have a section in the report that begins summarizing what the agenda item is, and then explains what the scientific use of the spectrum in that region is, and makes some recommendations on how to ensure that protection. So perhaps, Scott, if I talk through the figure first and then turn over to you so Scott's going to talk to the agenda items because many of them here are radio astronomy in particular. But I'll just introduce you to this figure. So this is a figure we produce for each agenda item. I'll circle back to the figures at the end. So here, this is in more detail. So this is agenda item 113, looking at direct satellite to cell phone communications in 694 megahertz to 2.7 gigahertz. So that's this large gray band here. What we've shown here in lighter gray for this particular agenda item is buried in the supporting paperwork for this agenda item. It says they only need to look at bands already allocated to IMT, given in a different document. Those bands are shown in pale gray here. And then, so here underneath, we've shown the nearby bands allocated to radio astronomy. If you see it in a dark purple, it means it's a primary allocation. So primary allocation, I imagine you're familiar, but just in case you're not, it basically means you have rights to receive and in theory transmit, but this is radio astronomy in this band without interference from anybody else, basically. Possibly if you're co-primary with somebody else, you may have to come with some agreement. A secondary allocation is similar, except you have to sort of suck up interference from a primary service, but you can expect protection from all other services. And then the pale signal here is just colors here is just where the band has been noted for you, that it noted somehow elsewhere in the radio regulations that it's used for radio astronomy. And typically that's RR 5.149, which says administrations are encouraged to take all practicable steps to protect radio astronomy. Similarly, in Earth remote sensing, we have some primary and secondary allocations there. And then there are a couple of 5.340 all emissions prohibited bands right next to where they're looking at doing direct cell phone to satellite to cell phone communication. So obviously that got our particular concern. But you'll see these figures later on, but I'll turn this over to Scott now for this particular agenda item.
All right. Right. So out of the 30 or so agenda items between Work 27 and the preliminary agenda items for Work 31 that we also looked at in this report, we've chosen 3 to highlight here in this talk to give you a flavor. And also we've chosen 3 that we regard as fairly important. As Nathaniel mentioned earlier, in the backup slides, we have similar slides for every agenda item we looked at. So if someone's particularly interested in the questions, we can pull those up. Agenda item 1.13 is one that we actually called out as particularly and immediately consequential from among all of those that we looked at. And this concerns, as Nathaniel was just saying, this direct-to-cell service provided from non-geostationary satellite constellations. And the reason this is particularly and immediately consequential is because it sort of removes the isolation that radio astronomy has been able to achieve de facto until now across these UHF and microwave frequencies here. Of particular importance for the radio astronomy service in this range of frequencies is this all-important 1400 to 1427 megahertz band that protects the atomic hydrogen hyperfine line. Atomic hydrogen is the most abundant component of the neutral interstellar medium. And so this is an extremely important line for radio astronomy. In addition, at 1.6 gigahertz, there's OH maser lines that are very important in radio astronomy. In Earth remote sensing, and then I should also say this entire band now is also becoming extremely important for opportunistic observing outside of protected bands of things like fast radio bursts and pulsars and so forth that are becoming more and more important in radio astronomy. So, for example, some of you may know about pulsar timing networks that are able to detect the gravitational radiation background through its effect on the timing, arrival timing of pulsar pulses. And that's done right across this band in broadband observations. In the Earth Exploration Satellite Service, as Nathaniel mentioned earlier, they piggyback on the protected band that protects the hydrogen hyperfine line to do soil moisture measurements because it's a frequency that's well suited for that and is a quiet band. And these measurements have applications to agriculture and food security and assessing Earth system changes, as the climate is changing. On the next slide, to give you a sense of how different direct-to-cell is compared to other satellite-borne radio communication services, we have this figure which borrows from a design originally by Harvey List at NRAO. And what you see here in the vertical axis is spectral power flux density, dV watts per square meter per hertz, and frequency logarithmic scale across the bottom. What you see in blue is the ITU RA.769 interference thresholds defined for radio astronomy continuum observations. Obviously, those are very sensitive to interference, so this is a very low level. The orange dots here are the RA.769 interference thresholds for VLBI observations, where the main concern is really just receiver saturation because the two distant telescopes don't see correlated radio frequency interference, and that helps a lot for being immune to a certain extent. The purple dots are from table 21-4 in the radio regulations, which are the power flux density limits at the Earth's surface for all of the present satellite services. And this extraneous purple dot up here that looks anomalously high is actually radar remote sensing. So that's why you see that up there. Now, compare this to this red box here, which is the direct-to-cell power flux density levels that are needed to support access to cell phones, standard cell phones with low-gain antennas. It's many tens of dB higher than anything else that has been coming down from the sky before. And as I said, this is going to pose a real problem for opportunistic use of the radio spectrum by radio astronomy, since nowhere will be remote anymore. Next slide, Nathaniel. So our key recommendations on this agenda item were that the same active beam synthesis technology that has really enabled direct-to-cell, as well as the satellite broadband like Starlink, should be leveraged to do things like avoidance of observatories and ideally nulling of transmissions toward specific protected locations, including radio astronomy facilities and radio quiet zones. Administrations, we recommend, should require such coordination agreements between the spaceborne direct-to-cell operators and radio astronomy facilities. And in fact, in the United States, where this is already happening, such agreements are being negotiated between operators and observatories via the NSF Spectrum Office right now. And finally, we noted that there are particular bands that we think it would be unwise to use for satellite-borne cellular service. And those are the ones that are adjacent to these 5.340 bands, in particular the band that protects the hydrogen hyperfine line. So next slide. Okay, whereas agenda item 1.13 is something that's happening right now, and in fact, in some sense, the ITU is sort of behind the curve. Like I said, this is something that's already happening in the United States and other jurisdictions. Agenda item 115 concerns communications in the lunar environment. So this is a little bit more future-looking. But again, it's of extremely high importance to radio astronomy because this agenda item is basically to start looking at what are the bands that are going to be used for supporting operations on the moon, and what will the rules be. And the reason this is important to radio astronomy is that the shielded zone of the moon is really becoming sort of the last accessible and truly radio quiet place from which one might hope in the future to carry out radio astronomical observations that are simply not possible from the Earth. Examples of such observations are those in bands that are used intensively by terrestrial active services, such as, for instance, just ordinary VHF radio and TV. Bands that are blocked by molecular lines in the atmosphere, such as those for water vapor and oxygen. And then any frequency below the ionospheric cutoff, which is around 20 megahertz or so. And so because in recognition of this, the shielded zone of the moon is granted special protection under Articles 22.22 through 22.25 of the radio regulations. The reason for that protection is that there's unique science that observations in these bands that you can't access from the Earth would enable. And this includes things such as observing important molecular lines right across the full range of cosmological redshift. Where like this, for instance, this hydrogen hyperfine line at 1.4 gigahertz, imagine looking at it through the depth of the observable universe, where it's shifted right through to VHF frequencies and beyond. Another example is observations of continuum and line emissions. It's just simply too weak to be observed from our noisy terrestrial radio environment. And finally, an interesting possibility is VLBI on an Earth-Moon baseline. So this is very long baseline interferometry, which many of you are probably familiar with, where you use telescopes at different locations on the Earth. You collect a voltage stream from each telescope, and you correlate them after the fact to produce very high resolution interferometric observations. And doing that on an Earth-Moon baseline would be a huge factor of increase in resolution. The Earth lets you get some thousands of miles. The Moon is 250,000 miles away, right? And some of these observations, and in particular the VLBI case I just mentioned, are very data intensive. So they will require broadband communications to bring this data back to Earth. So although the radio astronomy community has a stake in keeping the shielded zone of the Moon quiet, it's also a stakeholder in lunar communications. And so we're very interested in the development of high bandwidth communications from the far side of the Moon. Next slide, please. So our recommendations are that as administrations develop lunar communication systems, they should be flexible enough to move from band to band in order to move out of the way of phenomena that might prove very interesting to radio astronomy. So for example, if you notice some interesting, very weak spectral distortion in the cosmic microwave background, for instance, that might be revealing some process in the early universe, you might like to move everything out of that area and do an experiment that might integrate for some years from this quiet environment. We also recommended that optical wavelengths should be used for communications to, from, and within the lunar environment wherever possible. Thankfully, optical telecoms are becoming a mainstream technology and already used for backhaul in LEO constellations. We think that some particular attention should be paid to interference in the radio astronomy band at 2.7 gigahertz, because that's a band that would enable comparative observations between terrestrial and lunar observations. In general, we recommend to follow the methodology in RA 769 when quantifying harmful levels of interference, but that the factors such as integration time may be different from those that go into the RA 769 calculations. As we mentioned already, Article 22 provisions should be taken seriously. And because of the extremely potential for extremely sensitive observations on the Moon, there should be a very careful focus on out-of-band emissions and spurious emissions into the observing bands of future radio astronomy observations. I think we have one more agenda item to look at quickly. We realize we're going kind of running out of time. Agenda item 1.18 actually is directed towards protection of radio astronomy and Earth remote sensing. And this is because back in 2000, a number of bands that you see here in the purple and green boxes were protected for passive use in radio astronomy and remote sensing. And this agenda item basically is about the active uses in these gray boxes on the spectral diagram, basically having their rules sort of looked at to catch up with the protections that are afforded to passive use. So for example, you might notice in this diagram, there's kind of an anti-correlation between the purples and the greens, because where the, for example, at 118, where the remote sensing people are interested in oxygen, radio astronomers can't see through the atmosphere. So there's a sort of complementary protection. And the active service bands that this agenda item addresses are the ones that basically lie adjacent at the band edges of these protected bands. This spectral interval is extremely important to both radio astronomy and remote sensing, because this is really where most of the rich rotational spectra, such as that example that Nathaniel showed at the beginning of this talk, lie. And as well as continuum emission from the cool component of the universe. Likewise, these short wavelengths support the very highest resolution VLBI observations of energetic sources, such as active galactic nuclei powered by black holes. Many of you may remember the newsworthy images of basically the surrounding material around the black holes at the center of our neighboring galaxy M87 and our own Milky Way. And also the cosmic microwave background emission is 2.7 Kelvin, peaks at about 150 gigahertz. In Earth remote sensing, these bands are tied to particular molecular lines for the most part in the atmosphere that are absolutely essential for probing the atmospheric state, as well as window bands in between those lines that are selected to give complementary information like Nathaniel was describing. Next slide, please. So our recommendations here are basically to do as the agenda item says, which is to establish out-of-band emission, spurious emission masks for these active services that can meet the thresholds, the interference thresholds in the ITU RA 769 for radio astronomy in 2017 for remote sensing. Both, and very importantly, in aggregate, as we see more and more services that involve large numbers of transmitters, particularly in orbit, that are within the field of view of a given observatory, for instance, simultaneously. And finally, one thing that's often forgotten is that these remote sensing instruments require a cold sky view for their calibration. And it's very important to make sure that when a remote sensing instrument turns its mirror to get the cold sky view, it doesn't get blasted by downlink from nearby telecommunications transmitter, which could actually not only corrupt the data, but even damage the receiver. Next slide.
Great.
Okay.
I'll just quickly go through some closing remarks. Thanks very much, Scott. So just 2 or 3 minutes on some closing remarks, and then we'll certainly take plenty of questions. So one slide here on the common threads from our findings from radio astronomy. There's a growing need to ensure the protections of RAS observations by means beyond purely frequency-based allocations. The redshift from the expanding universe is moving signals way outside the protected bands. There's fast radio bursts that are currently unpredictable and unexplained, but as with pulsars, they may prove to be a really useful tool for unlocking new knowledge down the road. And we need cutting-edge observations of continuum sources require access to large bandwidths. Radio quiet zones have been an essential tool for attaining the access needed, but the rise in airborne and spaceborne transmissions threatens to undermine that hard-won and costly effort. But we can take advantage, as Scott said, of the beam steering techniques that have enabled these exciting new technologies from communications, and just make sure that we plant nulls in the right places. And that's, as Scott has said, is already underway on the US arena, and we really welcome and encourage that kind of engagement that's been taking place. And Earth remote sensing, in contrast with radio astronomy, Earth remote sensing sensors observe the whole globe, so any kind of geographically different approaches are unsuitable for their protection. And as Earth system science advances, so too the needs for more capable, more accurate, and more frequent observations becomes more important. And this is only going to be possible if it can guarantee interference-free access to the entire globe. And we talked in the past about maybe time sharing, because the current generation and the past generation of Earth sensors only went over any given point around 2 p.m. and 9 a.m., 2 a.m., 2 p.m. as well. 2 a.m. and p.m. and 9 a.m. and p.m. But we're now moving towards more continuous observations with constellations of LEO satellites, potentially geostationary. So we don't think that time sharing represents a sustainable approach for protection of Earth remote sensing service as the needs and applications for continuous Earth observations grow. One little aside here, I'll put it in this forum because it's perhaps where I get the most take up. The Python-based software used to generate the figures has been released as open source. It actually works. It digitizes the entire Article 5 of the radio regulations, all the tables and the footnotes and everything. And similarly, it can do the FCC document for the US allocations. And then there's a database that comes out and you can use it to query saying things like, show me all the SSF passive bands that are directly adjacent to primary locations to the fixed satellite service and so on. And then it makes those figures. I'd like this to be a resource for anybody who's interested in using it. I've released it as open source. There's a link here. If anybody wants to help me expand it, take over it from me, make it ready for the next core views report, use it in your SpectrumX work, do let me know. It might be useful in your community. So I'll wrap up here. Some other general closing comments. Given the advances in optical communication technologies and the large bandwidths they offer, we hope that we can use, we talked about how they should be encouraged in the lunar environment, but we think that they should be increasingly used for Earth to space, space to Earth, and space to space links as well. That will free up pressure on the radio spectrum for everybody, and thus perhaps allow more breathing room for radio astronomy and ESS passive. And then just circling back to Walk 27 in particular, as we discussed, many of the Walk 27 and the Walk 31 agenda items, which we haven't touched on here, have the potential to affect scientific use of the radio spectrum. And so we hope that by writing this report, we've given the people involved in the negotiations for those agenda items, some of whom I think are online today, we've given them some information on the value of these observations from a scientific perspective and some hopefully actionable information on how to ensure their continued protection. So I'll finish up there and thank Scott for his contributions. And I want to take the opportunity to thank all the people who authored the report, all the people who reviewed it, and thank you for listening.
All right. Well, thank you very much. We'll give you a round of applause here, and really appreciate the time that you both put together to come in and talk about these issues. I do have a number. Looks like there's a number of questions in the chat, but before doing so, maybe I wanted to poke at sort of something in your closing comment. You had talked about optical communications as an opportunity to resolve the issue. I think there's a lot of great opportunity there, as you pointed out. I think one of the challenges is optical isn't great through the atmosphere. It's great space to space. It's great in the lunar environment, but going space to ground to space, you have your challenges. And I think the other interesting challenge there is optical is inherently a point to point rather than a point to multi-point, right?
Yeah.
Kind of. I don't know if you have any thoughts on that. I just wanted to bring that up with regards to the solution space.
Yeah, that point is very well taken, and I recognize that it's easy to say this, and the cold reality may be harder to implement, but we just felt, particularly in the lunar environment, it was important to emphasize it there in what we said.
I mean, it absolutely makes sense in a lot of applications where you're not dealing with the atmosphere, right? And obviously the high throughput point to point. Absolutely agree with you there. So I want to go on to some of the questions that our audience submitted here. And so one of the questions came in here from Kevin Gifford asking about lunar planetary surface operations. So the cellular architecture on surface operations and sort of what frequency bands would radio astronomy prefer these surface networks to utilize. And I'll also ask, can you put that into the context of the shield zone of the moon and how that also maybe has an impact here? And maybe there's a question for Scott.
Yeah, I think that's not a question that it's possible to give a short answer to. And in fact, I think that Mike Mullinex in the chat is probably to some extent addressing that question. But that it's something where there would have to be a fair amount of study. But the other thing that, as we said in our recommendations, flexibility is also a key thing. And what we meant by that is not merely transferring the terrestrial off-the-shelf systems to the moon, but rather to really think about how to do this in a flexible way that would prevent any particular scientific observation from getting closed off forever.
Uh, I'll add that the agenda item, if you read our report in more detail, the agenda item listed a bunch of bands under consideration. And I think I'm struggling to find the exact thing, but I think we did sort of say, we agree that this band in particular is actually a good one to choose. I don't think we certainly weren't, la la la, don't talk about this for across the spectrum. I think we attempted to be conciliatory. But I'm not sure if that completely answers the question. But that's what I remember from what we wrote.
Great. So I want to ask a question, maybe in context of the WRC, right? So you've gone through this process, you've identified all the agenda items, you reported out on them with input positions. Maybe there's twofold. From a scientist perspective, I might ask, were your biggest concerns? And secondly, what type of work can the community do in terms of research efforts to better understand the challenges and to help provide science-based studies that can be used to make decisions?
So it's interesting. We had this question. What do we think are the most important ones? I think certainly the 113, 115 that we talked about. 116 also was on radio quiet zones. That was very specific for radio astronomy. The Earth remote sensing topics, I wouldn't say they're quite leapt out in the same way. There are a few that were of concern for ESS active, which arguably perhaps is less under threat. I mean, obviously not completely immune to needs for protection, but our main focus was we did pay attention to those ones, but I always feel that the passive observations are more vulnerable. And I wouldn't necessarily call out any particular agenda item as being any more deleterious to that than any other. Maybe that's just because we weren't didn't think it through enough or weren't plugged in enough, but we tried to treat them all relatively equally. In terms of what people can do, anybody is able to join the US Working Party 7C for Earth remote sensing, 7D for radio astronomy telecons. They happen on a sort of quasi-monthly basis, and they often have breakout groups. And I will say that science is generally underrepresented in those. There's a lot of representation for industry, including people on this call. And I think having more scientists involved would work. I will pay a call out to my predecessor as Corf chair, Lieve Van Zee, who tragically died last year. One of her last acts was to formulate and consolidate a group of radio astronomers who attend 7D on a regular basis. And that has been noticed. People like Scott and others have actually authored reports and recommendations that maybe it's just reports, right, Scott, that have made it into the ITU process. And that has made an impact. And I would encourage people on the Earth remote sensing side to get involved too. They can the process is get in touch with me, or perhaps Scott, Palo, you know yourself how to get involved and take part. It's a bit of a baptism of fire in the first instance, but I would encourage people to hang on, and I think interject with sometimes. I'm going to go out on a limb here and say sometimes facts take a back view to commercial expediency, and that is, as a scientist, I find that challenging to stomach. And I think if more scientists can get involved and raise their voices, I think that would help. I don't know, Scott, if there's anything you want to add on that.
Yeah, just as a general comment on how can the community protect science. I think what's needed is just for folks on the active side to first of all understand what the passive side is doing. I think many people do, but not everybody does. That it really is, as Nathaniel was describing, measuring the noise floor itself to very, very high precision, because the things that are being measured are the small changes on top of a big baseline, right? And then the second is to recognize the degree to which much of passive science has really made opportunistic use of the full radio spectrum outside of special allocations that, for instance, in radio astronomy, protect observations of the nearby universe, but don't protect observations across the whole range of cosmic redshifts, because that's not something that would be feasible. But we've been able to do this science because of geographic separation, and that's what's really changing now. And so the hope would be that the active community would see it as part of the technological development process to come up with the ways to provide selective geographic protection so that we don't lose scientific capability that we've had for decades and which is advancing rapidly.
Excellent. No, that's a great point. We have a couple minutes left. I'm going to try to squeeze in two more questions here before the top of the hour. Rene Leduc was asking about speaking about agenda item 1.18 and related to the recent FCC satellite spectrum abundance proceeding. It's looking to open more spectrum, particularly in W-band. She points out some of the specific frequencies. So I guess, can you comment or speak to this item, and maybe also agenda item 1.3 with regards to the spectrum satellite spectrum abundance proceeding?
I could comment on that because CORF has filed comments on this and they're public now. There are basically two issues that we were very concerned with. One, of course, is obviously the adjacency to Earth remote sensing bands. This gets back to making sure that the active services community really understands the sensitivity is for real. And that's why the out-of-band emission limits that might seem surprisingly stringent are really necessary. And then another issue that we flagged on this, which doesn't relate to agenda item 1.18, but which does relate to the W-band bands that are proposed in the satellite spectrum abundance proceeding, is it's going to be very important to look at second harmonic spurious emission from those uplinks, because those are going to fall all around the 183 gigahertz waterline and directly into some remote sensing allocations. And those are extremely important. And our feeling was that there may not always be enough due diligence on harmonic emissions, particularly at these really high frequencies before systems get deployed. And this is a case where due diligence is absolutely, absolutely needed.
Great. Thank you for your comments there, Scott. And I guess, unfortunately, I think we are not going to have time for any more of the comments that were posted, but I want to thank everybody for providing your input and your comments. We can share those comments with the speakers as well, and you're also welcome to follow up with them directly if interested. I want to thank everybody for attending our Spectrum X Radio Shop Chat today. It was very interesting, an important perspective. And we're looking forward to having you all continue to participate in future radio shop chats as well. So stay tuned. Make sure you track the newsletter or follow the website so you can get updates on our future radio shop chat. So with that, we will wrap up our session for today, and thank you everyone for attending.